Okay. So today we're going to continue our discussion of a topic we started on last time, namely the issue of calibration. So the process of calibration is one we noted is undertaken following model formulation, and typically involves trying to make sense of the diversity of information that we often will have on model emergent behavior of systems in the world. So empirical data we may have regarding high-level emergent phenomena within the world that cannot itself be used directly to estimate model parameters. Often we'll have empirical data that is the result of a wide variety of model parameters, rather than one parameter in isolation. And calibration is a process that seeks to make use of that data by trying to match model results on the one hand with that empirical data on the other. So, for example, we may be trying to match intermediate time series, observed data points at a very quantitative level, for example. In other cases, we may be trying to reproduce more phenomenological modes of behavior. For example, the fact that it's oscillating, or for example, the fact that women are infected far more commonly than men, or the fact that the rates are rising over time. These are things which are not necessarily specified with great precision, but they form important sort of observations about a system that you'd want any plausible model to stay true to which you'd want it to stay true. So model calibration can be, and often is, highly quantitative. We'll see that in our examples. But just bear in mind that often what we're looking at instead is reproduction of sort of modes of behavior. For example, we may want to see oscillations, even though we're not very particular about the frequency with which they occur. And in problem set 3, you folks will have seen a situation where we had empirical data on oscillations over time occurring in Saskatchewan associated with childhood infectious illness. And then you explored 2 different modeling strategies that tried to make sense of those fluctuations. And we weren't focusing there on point matching of those time series. So with a given time series, we might have had sort of mini outbreaks, every few years, and they were occurring with a fashion that was kind of somewhat irregular, but which involved larger outbreaks every so often interspersed with small outbreaks. Now, it could be a fool's errand to try to explain the vagaries of exact timing of these outbreaks. Typically there'd be too many factors outside the scope of your model to exactly predict historically when these high points occur, to the month or to the week or something. There's just too many factors outside of the model to realistically expect that. There's too many stochastics involved, which you can't predict. Things like vagaries of the weather in that year, etc. And if you were trying to point predict these things, you would end up boosting the scope of your model so large that you'd secure limited insight. If you ever got closure on the issue, it would take a very, very long time. So often it's best to put our efforts into things where we can make the biggest difference, aspects of model structure, and leave the vagaries of point matching out of our goals. And in that case, we may want to just capture this phenomenology that we see high peaks interspersed with low peaks. And really that was kind of the emphasis on that problem set 3 goal, sort of seeing if we could reproduce some of these phenomenology where we see really sharp outbreaks followed by low numbers. Okay. So just bear in mind, calibration, even though we'll be looking at kind of matching time series that are more gradual, often you will jettison point prediction and you'll look at internal matches. And it turns out there's some types of statistics, a particular type of statistics, Thiel statistics, T-H-I-E-L, I believe it is. I may have the I and the E reversed, but Thiel statistics try to quantify, for example, trends. So you can get a Thiel statistic that expresses the degree to which model trends agree with historic trends, even if they're off by certain quantitative factors, often in terms of degree, but both are heading upwards, for example. Other people have tried to quantify ways of spotting, okay, the model is oscillating and the data is oscillating, so they'll consider those sort of more similar. All of those things could in principle be built into model calibration. Some are more complex to try to match up than others. We're going to be taking a look at quantitative matching as our focus, in part because it's very common, and secondly, problem set 4, for those of you who are doing it rather than the project. Problem set 4 will involve some quantitative matching. Okay? You'll be taking an existing model for calibration and extending it to match additional time series. Okay, so well, we often have data from a variety of estimates for parameters. Often we don't have reliable information on all parameters. And I noted we often have data on emergent behavior of the system. It doesn't relate to any one parameter, but to a combination of influences. Sometimes this data gives us some of the dynamics, but it's not as broken down in as much detail as we need to put it directly into the model. So we want a model that stays true to this data. We want a model that accords with it, that offers sort of reasonable matches to it at some level, that is consistent with it. And to do that, we go to a calibration process. So I showed this graph last time. Here we have data from Saskatchewan, in fact, on a whole bunch of different factors. And we're trying to make sure that model results give us reasonable trends that match these. You'll notice the vagaries of the points here. So in this empirical data, sometimes we have values that are higher or lower. And not surprisingly, if you look at some of the margins here, you'll find that for the data that involves fewer cases, for example, it's more noisy. There's more sampling error. Whereas data that involves much larger numbers, there's greater regularity associated with it, and the noise is less pronounced. This is a well-known phenomenon. And in this case, we're matching the model with output from a system dynamics model. We're matching this data with output from a system dynamics model, and it captures the trends. Really, that's what we're looking for here. And it captures sort of the median, sort of, not always the mean, but fairly close to these values. And this is a result of calibration. Now, sometimes we are lucky enough that we may have data which we can use a process called backing out to break down this data and figure out analytically what the values of parameters will be. And often this process involves imposing some quite strong assumptions. So we may have to combine data from different contexts, for example. We may assume the system's in equilibrium. We may assume certain factors are independent. I don't know that I'll go into this in great detail, but suppose we know a couple of relevant factors like the breakdown of the population by sex, what fraction are male versus female, and we know a population-wide prevalence of diabetes, and then we know from some other source that, within this population, men are 1.5 more times more likely to have diabetes than women. Given those phenomena, they kind of triangulate. They allow us to figure out what the values must be. It's a matter of algebra. That's really what it is. And so we could set up this little problem, using these sort of constraints. So we know, okay, if we have some overall prevalence of diabetes that, 8% of Saskatchewan overall, Saskatchewan people overall are diabetic, and we have some count of males and females. If we know what that is, we know. And now what we are interested is PM and PF. We don't know them, but we know this must be true. That if we multiply PM times CM and PF times CF, this is the probability a given male will be diabetic times the number of males. Same thing with females, or the proportion of females and males that are diabetic, rather than probability, I should say. And then we do this for the whole total population. That must be true. And then if we know this ratio, we could substitute in and we crank through it and we solve for PM and PF. Folks have probably done that many a time in more courses than I know about standard algebraic computations. And occasionally we can do this. The problem is that often we don't have this information in exactly the right context. Like, we may know this ratio in a different province. And so we end up saying, well, we'll assume it's kind of similar here. And so it often ends up bringing in extra assumptions. And often there's some quite strong ones, like the models in equilibrium. The number of people coming into a stock is the same as leaving a stock, or what have you. But at a deeper level, when we're dealing with nonlinear models, nonlinear systems more fundamentally, their response to a given disturbance, to two disturbances, is not additive, for example. And often their response is something that is quite complex in how it involves a variety of different factors. If we have output from a nonlinear system and we try to turn that directly into understanding of parameter values, we'll often be rudely disappointed. It's a very, very, very complex combination of parameter values. We don't even have an analytic expression to express it. We have to run the model out. I won't go into this. Okay, so calibration is basically about triangulating from diverse data sources. It involves tuning the values of less well-known parameters to best match observed data. Okay. Best match observed emergent data, typically emergent phenomena that doesn't by itself tell us about one parameter. So we're often trying to match many time series at once. We saw that in that earlier graph. We're trying to match up, trying to accord the model against many pieces of time series. This is, by the way, quite different from a regression in statistics. With regression in statistics, we typically have some pattern. How many people have seen regression before? Okay, yeah. So you have some data, perhaps, on a relationship between educational achievement and income, or something like that. So maybe this is income here, and dollars per year, and this is years of education, or something like that. And probably this is not zero, but you can do a regression against this, and that there's two very big salient differences which stand out. Number one, you're specifying an explicit form, like this is linear, or this is log linear, or it's oscillatory over time, or what have you. But the point is, you impose an assumption explicitly about the form that you're trying to regress against. You're imposing an assumption about the form of the statistical model explicitly. In contrast here, the output of the model is only implicitly specified by the structure of the model. We specify the state charts. We specify the stocks and flows. We don't specify the behavior over time, and we don't, therefore, directly impose assumptions about how that behavior will change over time in an analytic fashion. And so here, we don't have the luxury of knowing ahead of time what our behavior is that we're fit. It's quite different from regression in that sense. A second way which is different from regression is here, we're often trying to match many time series, for example, many data points at once, rather than just one thing, say over time or over income or what have you. We may have many such different relationships to which we want the model to hold true, because it's a systems model. It involves a variety of factors. So we want it to match all of those simultaneously. So here we're trying to get the software. So those are two salient differences from regression. There are others as well. The idea here is to get the software to answer the question, what must the less known parameters be in order to explain these different sources of data that I see? In order to accord with them, to be consistent with them. What does that tell me about the values of parameters? Okay. And often this observed data is emergent. And as I said last time, this is often the point, the nexus of tremendous learning. Because often here we learn that the model structure we have at hand can't produce these patterns. So you folks may have gotten a sense of this a little bit in problem set 3. You could push and you could pull on some of the models you were working with, but there's a limited variability they're going to exhibit. You could explore a wide variety of parameter space, perhaps, and there's still going to be certain limitations about what it does. You can't twist it into any form. And often that's where the insights come, because you say, aha, this model structure can't explain this. Now, knowing what thing it is it can't explain is often really interesting. Maybe it can accord for this, and this, and this, and this, but this final thing, it cannot match. Aha. So that suggests to you there's something very, perhaps particular in the model missing. It suggests, it gives you food for thought to look into this issue more and to elaborate our model more. Remember, models are thinking tools. They help us think more consistently through the implications of our assumptions. And this, sometimes we discover that our assumptions are inconsistent with what we observe in the world, and we improve our assumptions. That, ladies and gentlemen, is a step forward, even though chronologically it may take more time. So, calibration here helps us find specifics for sort of a reasonable hypothesis that explains the data. This isn't necessarily the truth. What we get out of calibration is not necessarily the true situation, but it's often a reasonably good guess. At least it's upfront. It can't be ruled out obviously based on the data, and so it advances our thinking about what may be going on. Now, there's an interesting question. What if your model structure is wrong, but it's still flexible enough you can calibrate against it? Maybe it contains many of the factors, but not all of them. And when you calibrate it, you may get values for the parameters from that calibration that may be off from the real value, because they're trying to compensate for this other missing piece of structure, essentially. The parameters which are in your model may not be correctly estimated because you're missing a piece of your model that really should be there to best accord with the data. And so it ends up handicapping the estimates from other pieces of your model. That can occur. That can occur. You get distorted values for the other piece of your model. And in fact, we saw that a few lectures ago when we dealt with the issue of heterogeneity in networks. So often we'll have these networks which exhibit great heterogeneity. In human networks, often we'll see things like scale-free properties, where a few people have tons and tons of connections, and then a lot of people have just a few connections. And if we try to approximate this with with a random mixing assumption in a classic SIR sort of way, we assume people have a value of C. That's contacts per unit time. We assume that's pretty much homogeneous across the population, and we consider, okay, they each mix with people with a certain probability, etc. In this whole derivation that we ended up doing way back when for infectious disease models. This parameter C, if we try to calibrate our model to behavior that's resulting from a complex network structure, what we'll often see is that C, for example, is distorted. We will get a value of C that's much greater than the mean value of contacts per unit time in the population. We'll get a value of C that implicitly, ladies and gentlemen, builds in a knowledge of network heterogeneity. It builds in the fact that it tries to compensate for the fact that, okay, we're kind of assuming homogeneous mixing, and it needs to be larger to accord with the data. So it's a lot larger than it really should be given its strict interpretation, which is mean contacts per unit time for people in the population. So this is an example of a situation where a model missing some structure, in this case network structure, ends up compensating the value for a parameter, this being an aggregate model. Does that make sense to people? Oh, sometimes parameter values, if you're missing structure in a model, the parameter values that come out of calibration may be off. Okay. At the same time, calibration helps us leverage a large amount of diffuse information that we often have at our disposal, and which can't be used to directly parameterize the model. And it helps us falsify models. It's a step. It's a step towards it. It's imperfect, but it's often a key ally in trying to falsify hypotheses. And I don't know the number of times where I've taken a model, tried to match it, ended up having to modify my assumptions to adequately account for the different data that's available, having to sharpen my assumptions about what's going on. Okay, now how does calibration work? Calibration uses a global optimization. How many people in here have been exposed to optimization before? Okay, a little bit. Okay. So the idea here is that we are seeking out a combination of parameters that minimize some discrepancy between model results and observed data. Okay? Qualitative, quantitative, in some cases, either qualitative or quantitative. The data, often in the form of time series, this says forms. It's really not forms, it's really informs. That's a better one. It informs the objective function. The objective function, the thing we're trying to minimize in this case, we can think of it as discrepancy. It takes into account the data that we're trying to match and tries to match the model data to that. And the optimization algorithm here typically will run the model many, perhaps thousands of times, for example, to find the best match for all the data. Okay? It's going to try to find data that matches it. Okay. What information do we need to specify for calibration? Well, we need a couple things. Specification of what we want to match. What are we trying to match up with? And if we have multiple things we're trying to match, how much do we care about each of them? Okay. We need to specify, partly as part of that, sort of an error function, or a discrepancy function. It tells us how bad our match is, a given match is, how bad to consider this, basically. The alternative is you try to maximize a payoff function or objective function, but I'll prefer here to think about it as a penalty function, discrepancy we're trying to minimize. We need to have a statement of what parameters to vary over what ranges to vary them. We may be interested in some characteristics of the optimization algorithm. Okay. For example, we starting from a single point. So here we're exploring the space. I showed this slide last time. We're exploring the space, trying to find values of mu, tau, and beta that best accord with our historic data. And we're exploring it artfully. We're exploring it in a judicious way that builds on our, for example, past understanding, perhaps, and it isn't just exploring it willy-nilly at random. Instead, it's recognizing gradients and going in the direction of gradients that perhaps decrease the discrepancy the most. It's recognizing perhaps past areas of space which have been very advantageous and perhaps builds those into new areas. So, for example, AnyLogic's algorithm is much more advanced here than Benson's current algorithm, and it makes use of what's known as genetic algorithms. So it's using sort of the analogy is to genetic encoding associated with characteristics. It takes past successful things and breeds them with new successful ones to find combinations that are successful, that may be successful, etc. Okay, and here we're trying to improve the goodness of fit, or trying to reduce the badness of fit to the observed data. And to do this, we're going to have to quantify this discrepancy, okay? So for each historical data point, we're going to calculate some discrepancy of the model. We're going to figure out the absolute value of discrepancy by comparing historic data models calculations. And for reasons we'll talk about in just a sec, we're going to convert it to a fraction value and sum this out. Okay. Now, if we're keeping track of discrepancies, there's a number of metrics that are quite desirable for these discrepancies. One is that they be dimensionless. I've introduced the notion before of dimension. I don't like that. They should be of unit dimension. Why should they be of unit dimension? Let's suppose that we're trying to match the output of our model to data about cost over time, about number of deaths, and about number of people with the illness or something. Why would we want the discrepancy metrics used for each of these to be dimensionless? To have unit dimension. Something like a fraction or something like that. Why would that be advantageous? Sorry? Yeah, it scales. You could think about it in that in a way in terms of that. Someone else? That's right. Yeah, and I think that gets into some of what Seth was saying there as well. There's another side to it is, okay, so suppose I was measurements of dollars that were in the billions, and the number of people, deaths that were in the hundreds or something like that. One issue is, okay, I don't want to be comparing, saying, okay, we're off by 0.1 billion, so we have to minimize that at the cost of having huge errors in deaths proportionally speaking. Being 10 times off in the number of deaths, well, it's still smaller. Perhaps you have deaths in the tens, and 10 times off is 100, and it's a lot smaller than 0.1 billion. So we'll just try to maximize the best fit to cost. But the other thing is that it doesn't make sense to add a discrepancy of cost to a discrepancy in people, or people per unit of time. They're different sorts of things. And we can't say we're 10 people plus, $100 billion off, or something like that, as an additive thing. If we're going to end up with a single discrepancy metric, a single number that summarizes our badness of fit, we want to do so in a way that combines all the results of others, of each of the discrepancies. And the way to do this is to make them of unit dimension, because we can add those things up. We can say fractionally, for example, how far off are we in terms of dollars, how far off are we in terms of people, and we can sum those up because they're dimensionless. Does that make sense? It's independent of units as well. Doesn't matter if we're measuring people and hundreds of people or thousands of people or on a per person basis. So it's independent of units, and it's independent of the dimension. We'd like it to be weighted. We'd like to be able to say, however, that we care more about matching costs than we do about matching kind of deaths, for example. Maybe because we think the data on costs is more reliable. So we'd like to be able to provide some indication of relative importance. For tractability, sometimes we'd like it to be able to be an analytic function. We'd like to be able to differentiate. We'd like to be able to make it smooth and tractable to reason about, for example, its extremum by differentiating it. When is it a maximum or minimum? Ideally, that would be a nice property. We'd like it to be concave. This is a non-obvious property, but two small discrepancies of size A, say with respect to different attributes, should be considered more desirable than as we might say, robbing Peter to pay Paul. One big discrepancy with size 2A for one, and no discrepancy at all for the other. We don't want to just say, oh, what the hell, we're just matching costs, and the deaths will be quite off, but we can get cost to 0. Normally, we'd like to kind of get both to be kind of half off rather than giving all of the benefit of the doubt to one rather than the other. We like it to be symmetric. So if they're off by a factor of 2, it shouldn't matter if it's off on sort of half of the appropriate value or 2 times the appropriate value. It should be non-negative. No discrepancy in one thing should cancel out a discrepancy in the other. That would be kind of weird if we consider some discrepancies negative. So if you have a discrepancy in people, it eliminates the discrepancy of cost. And finite input should yield finite discrepancies. So these are some characteristics. And here's an example of a discrepancy function matches all, for example. Here we have some historic data minus model data, whether it's this or the reverse doesn't matter because we're going to be squaring it, divided by the average between the two. Now, this is good if you have H and M both being physical quantities that are 0 or more. So the denominator is only 0 if H and M are both 0 in this case. If H and M are constrained to be non-negative, the only way this can be 0 if both are 0, in which case this is 0, in which case there's get treated as essentially no discrepancy. And here, because the model will be matching the historic exactly, we have this squaring property, which means that it's concave. The further out we get, the worse it gets. So it's going out from here, it gets worse. So we'd rather have 2 small discrepancies than one very large discrepancy. It's analytic. It's dimensionless. Why is it dimensionless? Anyone? Why is it dimensionless? We have historic, say, cost minus model cost over some of these. Why is this dimensionless? Because it's canceled. Beautiful, beautiful. Thank you. So the model units do cancel due to division. So W is a weight. It's a weight that we can attach, and we might want different weights for different time series, whole time series, or we might even want different weights for different data points. So maybe there's some data points which have larger sample size, in which case we may weight them more highly because we believe statistically they're better grounded. Okay. So for all these reasons, it could be desirable. And for weight, we might weight things more highly because we care more about it, because the purpose of the model, this is model focused on cost, and matching up the size of the population is desirable, but being off a bit in terms of that is not as critical as being off in terms of cost, perhaps, for our purposes. We might weight it more highly because there's a varying uncertainty in our estimate. The more uncertain the estimate, the lower the weight might be. And sometimes we have quite principled ways of, for example, making the weight depend on the variance of the appropriate estimate. And then whether data exists. So for example, we may have a discrepancy function, and there may be missing data for a certain data point, and we just give it a weight of 0, and then we don't care about that year as far as considering that. Okay. So in terms of the optimization, Vensim, for example, is a very simple optimization algorithm based on what's called Powell optimization. It's basically a scheme that's sometimes known somewhat confusingly, if we're thinking about minimizing discrepancies, known as hill climbing. But really, here it's sort of valley. I don't know how to say it. Valley spelunking. Beautiful, beautiful. A well-chosen word. So it's spelunking. We're trying to find the deepest place within this discrepancy space, and it's very naive in the sense that it is using only local information, and we can get stuck at local minima. So we can, decline for a while. So maybe it starts atop my head, and I won't have you conjecture on the shape of my cranium, but it'll sort of end up, going down a certain distance, then going down, and maybe it gets in the seat of this chair, which may have a little depression in the center. It's actually a bit of a saddle point, but it goes in the center of this chair, and imagine there's a depression here, and it may sit there without realizing that all it would take is a small perturbation, and it could go down to much lower levels. So this spelunking is a signally myopic spelunking, which is a dangerous sport indeed. Myopic spelunking. I would not recommend engaging in it if you have myopic tendencies, absent your dry whip. So we may go down to a local minimum, and we'll sit there for a long time. Well, or we just give up the search. We say we have achieved the objective. We've gone down to the minimum point. So the way Vensim deals with this is by starting off at different random initial points. So maybe this time it declines my cranium and falls down here, but another point it goes down my ear and goes down to the floor, something like that. So here we start at different points in the space, with the assumption being we may get down to different different points in terms of the minimum. We may get down to more global minima, for example. And so with Vensim, it can run this. Often with a system dynamics model, it's quite quick to run this. So we might run 1 million simulations, 1 million different iterations with different parameter values. It's deterministic, remember. It's a big difference from, say, AnyLogic with an average models. It's deterministic, so we're in Vensim, so we're going to be getting the same result every time. So we run it once with each set of parameter values, and it's adjusting the parameters, running the model, recording the error function, finding the gradient, the area, the direction of steepest descent, and it's going to be declining down that until it can go no further, until there ain't no way down that improves it a lot, in which case it will declare victory and start over again. At least that's an option, or you could have to just say I'm done. A classic way of dealing with the problem of local minima is by adding randomness. This is one of the areas where you add randomness to an algorithm that can actually help a little bit of them. This is more obvious than a lot than most of them. So here we add some heat. So there's a thing called a Boltzmann machine, which is sometimes used. You have greater amounts of heat up front. If any of you have seen simulated annealing, which is a really heavy-duty optimization technique, there's lots of heat up front. Things bounce around in really excited ways, so they're less likely to get stuck. And then over time, the amount of heat dissipates, and so you'll stay more and more sort of within your region. You'll be less and less likely to be knocked out of a good region by chance. So it turns out that global optimization is an area of a lot of interest, and in recent years has gotten injections of insights from things like genetic algorithms combining together in a genetic sort of way the best previous occurrences, which may occur in different areas of space, swarm-based methods where you have multiple particles going over the space at once in some way that exhibits collective intelligence, etc. So I'm going to open up, if any of you have your laptops, you're welcome to do this. I'm going to open up something called SIR agent-based calibration. And we're going to see how this works in AnyLogic. SIR agent-based calibration was one that we opened up last time. It was one which we particularly used to examine parameter variation experiments. So some of you may remember this experiment we ran last time, where we were examining impact of, in this case it's just stochastics, in other cases it was changing parameters. Anyone want to conjecture why you see these two bars going on down here? So it reports the number of runs here. You'll notice it's going up by 2 at a time for the most part. It's 2 cores, yeah. And if it were 4, it would be 4 at showing response to 4, etc. So it ends up taking advantage of what we call the embarrassingly parallel nature of this. And this is actually an important point for those interested in computational science. The fact here is that when it comes to sensitivity analysis, cases, for some aspects of calibration, we're dealing with problems that can be parallelized really, really easily. They can be mapped out to multiple cores, mapped out to multiple computers in a farm, in a cluster, for example, very readily. And this is one area where the advances in computer speeds haven't been blunted as much as they have been, say, in single core speed. We could still get a tremendous amount of speed up if we have a large server farm at our disposal when we run some of these things. But I've asked you to open this up, SAR agent-based calibration. It's in help example models, and then just in the list of models to the right, I believe. And this time, for today, we're going to go to a separate one. We're going to go to the calibration experiment here. Now, the calibration experiment, we're going to start by running it. And what you'll see here is that it's placed some historic data on this slide down here. You folks who are planning to do assignment 4 will become quite familiar with this depiction. And you'll be building atop this, so it bears additional attention. So here we have historic data, shown here in the lower right in yellow. Take a note of that color. And up here in the upper left, we'll be seeing, as well as the upper right, in the upper left we'll be seeing reports on the iteration number, which replication within the iteration, which realization within a Monte Carlo ensemble, a collection of different realizations we're currently running, and then what the value of the objective function is here. Now, they're using, in this case, the objective function to mean something we're trying to decrease. Okay? In other words, it's something that we are, it's a penalty function or energy function, something we're trying to minimize. And you'll notice it also reports the best. So we're going to be exploring space, and there's no guarantee our current one is the best one. We may have seen the best earlier, but we're still exploring other areas of space, which in the hopes that we'll get to an even better one than the best so thus far. And meanwhile, on the right, we will see a visual depiction of this process of reducing the objective function over time. So we'll see how the discrepancy function results are decreasing over time in response to our exploration. So here we can do run calibration. And you'll notice down here on the lower right, it's actually trying to fit different curves with different parameter values to this actual value. Up here on the left, we are seeing different iterations, replications within iterations, and objective functions secured. You'll notice the best one thus far is number 5. That was this one, I believe, here. This may be starting at 0. In any case, I think it's maybe it's this one right there. Even though confusingly, it's shown different. This is different iterations here, and we have the current output. So it's exploring some different ways of trying to adjust the parameters to match this. The red here is that best one. You can see it's doing okay. Now, you'll notice over time, early on, it really declined dramatically. And we have yet to beat this number 5. We've yet to equal what we achieved in the 5th iteration. You notice that in subsequent ones, we've been all over the map in terms of the success of these subsequent explorations. These subsequent sort of candidates where we're trying to find the better one. It's exploring the space not in a continually decreasing way. If we're continually decreasing, we kind of expect it to be decreasing over time. Instead, we're exploring it in a way that involves quite a bit of stochastics. So we can run this thing for quite some time. Suffice it to say that it will try a variety of values, and eventually, there's little doubt in my mind that it will improve upon this. So here we have the output, and eventually, you see it's getting close with some, to exceeding it. So, I'd like to talk about the mechanisms behind this. It's an enticing display, but there's actually quite a bit of thought that goes into making this possible, and some plumbing to hitching it up. And ladies and gentlemen, let us explore. Just after it's hit number 97, which exceeded the best, which is the best value thus far. Yeah. Okay, so let's go see something about how this works. And you notice it's bang on right now. It's bang on that historic data. So there may be some questions in your mind about what's going on here, as well there should be. So let's talk about properties of this. So I'd like you to go click on the calibration and call up the properties of it if you have this open. You'll notice there's a number of attributes that we can specify here. So there's the normal stuff we tell for an experiment, such as what its root class is, the main class of which it depends, etc. And then it's going to ask, okay, for random numbers, do I use a custom generator, or a fixed seed, or random seed? Normally you're going to make use of a random seed if you don't provide a custom generator. Okay. And now the key thing is going to be the objective function. What are you trying to minimize? And we'll come back to this, but this difference method essentially takes the Euclidean distance between what we're trying to match on the one hand, DS infectious historic, and DS infectious current. You'll notice that we constrain it to lie within a certain number of iterations. We can make that very, very large, obviously. Or we can ask it to stop automatically based on some statistical criteria. Alex, yes?
Does the number of iterations, does that matter with the number of cores, or just try to spread the work?
Go spread the work.
Okay, so it'll always do 500 iterations.
Yes, but that's my understanding. It's not like it'll.
If there's 2 cores, it'll do 1,000.
Yeah, no. I think it'll farm them out. It will do load balancing, as we put it in computer science, to sort of spread out the computations among the different cores and just keep on keeping them busy until all 500 are done. Okay. There's this automatic stop, which will be based on statistical criteria. And here, ladies and gentlemen, is where we're specifying what information we're going to be varying. So how are we going to vary the underlying parameters? Okay. That difference function that we saw makes use of a built-in call to a built-in method. There's nothing privileged about it. We can write our own difference function. In fact, earlier versions of AnyLogic you had to. What this is taking is a difference of these two data sets. I sent you folks last night a reminder of a site where I have extensive hands-on lectures which explore, for example, data sets, how you collect data in AnyLogic, how you output that data, some discussions of debugging in AnyLogic, and particularly for those working on problem sets where you get stuck, or projects that might be useful references. Hence my sending it out again. But suffice it to say that you have these very readily used data sets. We saw them once or twice in class. And here you can call a difference, and it uses a Euclidean algorithm, a Euclidean distance algorithm. So square root of the average square of differences between the two data sets. Okay. Now, you may be wondering, where is this DS infectious current coming from, for example? And we're going to go see that. Okay, so we can write our own difference function here if we want to. Define our own difference and call that, for example. And, for example, sometimes perhaps despite my paeans to having analytic functions, you may want to use abs, absolute value. Abs is, it took a computational physicist to warn me against abs one time. I try to avoid using it because it's kind of a non-analytic function. It's not differentiable. It exhibits sharp discontinuities at 0, right? In terms of its first derivative, so its first derivative looks something like, you know, it goes initially at sort of so essentially we have this situation where it goes from -1 to 1 at 0.0. So this is a sharp discontinuity, and in general, it's preferable to use a square because it's also concave. But if you want to do it with abs, you can do it in this sort of way. Write your own function. So how are these mechanisms incorporated? Well, some of this will be useful for your problem set, so I'll briefly go over it. The data set of DS infectious historic is going to be populated from what's known as a table function. A table function in AnyLogic basically provides you a way of characterizing a function from some input to some output. It's a function defined numerically. And one of the nice features of it is that it can interpolate. So for example, and extrapolate as well. So you can say interpolate, for example, linearly, or interpolate with a cubic spline, and it will take care of that for you. Okay? So if you have some data that you wish to feed into AnyLogic, and you know that data at several points, and you want to be able to evaluate as a function of this domain, as specified by the input here, at any point, not just the points you specified. This is a very convenient mechanism to use. You can also go just, if you want to copy from Excel, for example, paste into this, you can do so quite readily and populate it. So you don't have to type this in. So it's a labor-saving device, like a lot of AnyLogic's mechanisms. Quite useful for that. So here we're specifying the historic data, and then we have a little call to the data set saying, hey, fill from this table. Just fill yourself from this table. Fill up the data in this data set from there. Okay. So that's going at the time this experiment starts running, because that data historically is not going to change between iterations of this optimization. It's not going to change with each successive run of main. Okay, now, some of the things that one or two of you might have been thinking about, if you're thinking ahead here, is that we're doing here an optimization that's quite different from what we do in Venn, not only in the simplicity in terms of the sophistication of the algorithm used for optimization, but also the fact that we're dealing with stochastics. So we are operating in a space, and maybe to make this point, I'll just go back to this this cube we have. In general, this is a d-dimensional cube, right? Here it's 3. In general, it's going to be d dimensions if we're doing calibration with respect to d parameters. Now, if we were doing this with an aggregate system dynamics model, most traditional system dynamics models, while you can do stochastics in Venn, Sim, or AnyLogic for system dynamics models, traditionally they're deterministic. And what that means, if we evaluated the model with a given set of parameters, we ran it out over time, we'll get a deterministic result. So if we ran it again with those same parameter assumptions, we will get the same results exactly. With an agent-based model, a discrete event model, that's not going to be the case. For a given point within the space, ladies and gentlemen, what we'll have is not a single value, but a distribution of values at a given point in the space. And if we wish to optimize in a space like that, such as that, a space where we have these stochastics in response, to develop confidence that we're not over-responding to vagaries in the response. So we just weren't really unlucky. Maybe we had the best combination of parameter values, but we rolled snake eyes, and we were told that the result is a very poor match, because when we ran the model, it happened to exhibit stochastics in just the way that, is the opposite of the historic data. And so it looked like it was far off, where really those are the best parameter values, and it was just luck of the draw. So typically, when we're exploring this space in calibration for a stochastic model, we need to account for the fact that the space exhibits distributions at each point, and we want to draw not just once from that distribution, but multiple times. We want to be more robust, given the vagaries of variability in results. We don't want to be thrown off from really good parameter values by just one bum run of the bum realization in terms of how well it matches. Okay, so let's talk about this here. How are we going to deal with this? Well, these stochastics are quite well rooted. We can't just suppress them. In calibrating an agent-based model, we want to avoid attributing a good match to a set of parameter values simply due to chance, or ruling out some due to chance. To reliably assess, what we're going to do is we're going to go to the Monte Carlo strategy. We're going to run this model multiple times over for a given set of parameter values, run multiple realizations with different random number of seeds. And then, for example, we may take the mean fit of this realization. Now, it's worth reflecting on the fact that what we're probably observing in the world is a single realization of the world. We're not looking at the mean of the world, the mean over many possible realizations of the world. We're looking at one particular realization. We see certain stochastics over time that are indicative not of mean behavior, but of in fact, the full variety of variability associated with the stochastics. So this choice of mean is not necessarily what you want, and I think that's actually worth some thought. Maybe what you want sometimes is the max fit, the best fit, you've gotten from your set of options. That's worth some thinking about. Let's see how AnyLogic does this. So the truth is that AnyLogic has a hierarchy to deal with this, but its terminology is confusing and, truth be told, somewhat inconsistent. So at the top of the hierarchy, we have an experiment. And as an experiment, as we saw last time, can involve multiple runs of scenarios. It can involve multiple runs of the underlying model. Right? Now, an experiment, for example, could run multiple simulations with different parameter values. Remember we saw that last time with parameter variation? It ran the model with multiple different parameter values. It ran it in a grid, for example, or by drawing them from distributions. So there, an experiment ran simulations, right? It ran multiple simulations, multiple scenarios, we could think of them, and think of it as. Now, that is not, ladies and gentlemen, the lowest level of this hierarchy. AnyLogic provides a further way for within each simulation to have what it calls replications. I prefer the term realizations. And so here, realizations. So here, a simulation, which I prefer the term, and I'm going to just denote it here, scenario. Perhaps that's closer. This doesn't always correspond, so I should probably say e.g. But it's one particular case where these really make sense. So we have an experiment that's running a bunch of scenarios. Each scenario is associated with a particular parameter vector, a vector for the parameters we're varying. And for that particular parameter vector, we run multiple realizations. Oh, look at that. Oh, okay, yeah, that's right. I almost reacted to myself adversely. So we have multiple realizations, within that, which AnyLogic called realizations. So we might have 10 realizations to deal with the stochastics for this given set of parameter values as captured by the simulation, which I think of as a scenario. And all of this is going on with an experiment. So the experiment may run hundreds of simulations, each of which run, say, 10 replications. Okay? Questions on this? Unfortunately, you're going to see this terminology reflected in some places, and then occasionally it will be thrown out in AnyLogic's interface, and another terminology will be used. So, I think you're going to, you may see that in the coming minutes. Okay, so you'll notice if you go to the Advanced tab of this experiment, this calibration experiment, you will see a bunch of factors, a bunch of code. And I want you to be able to parse this code, because this code will be useful, among other things, for problem set 4. This code will be directly useful to understand what's going on. So forgive me if I go into it in more detail than I normally would. Okay, so what's going on here? Well, we have some places where we can specify additional class code, like imports and stuff like that, declare enums up in this additional class code. But here, initial experiment setup, we have a place where we can put things that get done once when the experiment, ladies and gentlemen, as a whole is being set up. And here we're populating data from this table function into our data set. Make sense? Okay. Now, before each run in the experiment, read associated with a this, when it says experiment run, we're talking actually about a scenario here, with particular sets of excuse me, I stand corrected. No, excuse me. This is before the experiment as a whole is run. Then we basically reset our best objective and the best feasible objective we've seen. Okay. So we sort of clear out all that sort of information. Now, after each, this says simulation. Really, it's talking about the realization. Okay. What's going to happen is this. Now, we saw this something very similar to this last time, and I would like you folks to answer me. What is this doing? What is this root? Who remembers what root is? Yes. So what's going on just before this is that it's run this simulation in main, because main is the one responsible for actually doing the simulation. So the experiment has told it, main, hey, main, create an instance, okay, with these parameters. And it tells it the parameters. Use these parameters. And then it runs it all through. Now, in the process of running it, that main instance is accumulating something in a data set called DS infection. Do you remember that? We saw that last time? In main, up in main, there's a data set called DS infectious, where it's storing up its number of infectious individuals for different points in time. So for those who don't remember that, if we went down here to main, and we went to analysis data, we could go look at this, and what this is doing, it's sampling from this variable every 2 time steps. Remember that? We saw that last time? Okay, so main has computed all that. Main has run through its life based on the current set of parameters. And now what this is doing is it's retrieving that data from that. It's salvaging it from main. Why is it salvaging it from main? Why is it taking this out of main? Main is going to get deleted. Main is going to be deep sixed. Main is going to be disappearing. We need to get that data out of there before it disappears. Right? Now, using that data, we are then going to say we're filling this data set from there. Where does this data set live? DS infectious current. It's inside the calibration experiment. Remember, the experiment here lives beyond instances of main. Remember I made a quip about empires rise and fall, all within the span of the experiment? The experiment is the overarching structure. The experiment is what's accumulating data all throughout it about what what has been going on with successive runs of this model at the realization level even. And so it's salvaging this remain, and it's actually recording it away in its data set for now. And then what it's actually going to do is it's going to be using the objective function, ladies and gentlemen, and we'll go to this. It's actually going to be using the objective function here, right here, to perform the calculation of the objective. Okay, calculate that objective. Now, what's left hidden here is actually the how each realization is going on. But this is actually, sorry, how each the results from the realizations are being packed up to the results for the scenario, or what it calls the simulation. And that's associated with this after iteration code. So after it finishes all the realizations for a given, what it calls simulation in that hierarchy I talked about earlier, what I call a scenario. In other words, after it finishes all the realizations for a particular parameter vector, a particular assignment for each of the parameters we're calibrating, then it's going to ask, okay, is the value of the current iteration the value of the best that's been found so far? If so, we're going to fill this data set that's indicating what the values are that we're seeing over time in terms of the number of infectious individuals. And filling this data set, ladies and gentlemen, is going to update that graph. Do you remember that graph we saw? That graph of sort of the best fit thus far, that's coming from this thing here. So that's where we're getting the data necessary to plot that out, for example. Okay, so we're saving away that result. Now, I showed this before. So this graph here, the red, is going to come from that DS infections best. Okay. And actually, it's updating some of these things first. Now, one thing you will see, ladies and gentlemen, I'll just poke around this user interface here. So first of all, you may want to take a look at this. Excuse me, not this graph, but the graph below that. This one here. You'll notice that this is graphing several things. One is this DS infectious best. That was the red, right? That's why this is red right on top of that. So that's what that came from. The more interesting thing is up here. If you go and look up in this region, what you'll see is there's a small text box there, and that text box is actually ends up being set. Okay, it's actually not declared, or is it declared dynamically? I think yes, it is. There we see. Now the fox has shown its tail. So this text, these are the dynamic properties associated with this text box. What do I mean by dynamic properties here? Who remembers where we've seen this before? Back many weeks ago, we used dynamic properties for a different purpose, and I think in your problem sets you would have used them. Yeah. So basically, the dynamic properties state properties that need to be maintained automatically by AnyLogic, and in this case, the value of the text is one of these things that gets updated automatically. What it's doing, though, is it's saying get best parameter value. So the value of this text for the contact rate is based on get best parameter value OQ var contact rate. Okay, and that may seem bizarre. And if you go poke into it, OQ var is basically OptQuest. It stands for the optimization engine that's used by AnyLogic. And this is an encoding of the particular parameter that needs to be retrieved from the name of that particular parameter. And so it's calling off the get best param value, which is defined, I believe, in the OptQuest engine. So this is actually, you have to realize there's a few points where this code is interfacing with the so-called OptQuest engine, and this is one of them. Okay. So get best param value is something that calls off to OpQuest to update this information. Okay.
The get best param value. That's that part of the optimization engine itself.
So get best param value. The optimization engine does record the information on what the best parameter value function. So you see this is part of this OpQuest variable. It says return the value of the given optimization parameter variable to the best solution found thus far. And just be aware that there's a few places where if you need certain types of information, we didn't need that to display, the results. And I might add, we actually don't need to do that strictly. The fact that we've called off to do this is a convenience. We could have recorded that. Well, where could we have recorded it? Where else could we have recorded away the best value of the parameter thus far? Or the value of that parameter at the point that yielded the best result thus far? Where could we have stored that away? Yes, in the experiment. So specifically earlier, right here, we could have remembered away what that value was. It's just that certain types of information are available through OpQuest Optimizer if you wish to ask it, but I have barely interacted with it at all because a lot of that is readily obtainable from this context.
Would there be a race condition if we were trying to maintain the value ourselves as opposed to asking the optimizer? Because it does run
That's a good question. So would there be a synchronization issue type of thing? Good question. Very good question. I think it is thread safe, but I'm not. I can't speak to the thread status of this. I have to look into it. One could make it thread safe by posing a synchronization block, but synchronization mechanisms. Okay. A few other things here that are conceptually important as well as about the plumbing. One thing is that often you will find that there are situations where you want to rule out certain parameter value combinations. So you may say in general, I want this parameter to vary between A and B, between 0 and 1, this other one between 10 and 100 or something like that. But it may be that certain parameter values taken collectively are incoherent or not possible or what have you. And so you can specify constraints and simulation parameters. These are expressions that test the validity of the particular combinations. Okay, and that's useful. That's a very useful thing to do. Sometimes it's not so much any one parameter value that's off, but these two cannot be equal, for example, or they should never sum to more than this third value or something like that. So maybe you want A and B to vary within ranges, but they always have to be less than C or something like that. And sometimes you can formulate ways of deriving one from the other, but sometimes it's just easier to sort of rule out that case. These are tested, ladies and gentlemen, before a simulation runs. By contrast, and this actually links in a little bit with an issue we're talking with one of the students here, Seth, earlier this afternoon. Sometimes you do a run with the simulation model, and you find that there's some aspect of the run output that marks it as clearly infeasible or unphysical or impractical or makes it unworthy to consider as a simulation run. And so here, these are so-called requirements. These would be things that you would test on the results to establish face validity about whether we should even consider this a legitimate run. So maybe, for example, in a system dynamics model, the stock goes negative, or it should never go negative. And it's a matter of numerical instability. You know it's to be ignored, and so you basically impose a constraint that it has to be within this range, and you just throw out those that go outside those ranges. There may be better ways to deal with it, but this is this is often quite useful if you have a complex situation and you only want to consider certain lines. Does that make sense? Okay. So I contrast optimization constraints, test and legitimacy of parameter values, and optimization requirements, the sense validity of emergent results. Okay, now coming here towards the end of this, we have in the replications area of this experiment a choice of whether we want to use multiple realizations. And there's a checkbox. And if we select this, we could either select a fixed number of replications, and I think right now it's at 10 on mine, in which case, ladies and gentlemen, it will always do the mean of those. Not always viewed as desirable from my perspective, that it always takes the mean. If you're doing 10 realizations, it always takes the mean value of their matches, of their discrepancies, to determine the discrepancy for the entire. Or we can do this not just based on a fixed number, but a varying number, and basically it stops replications when a certain confidence interval lies within, when the confidence interval lies within a certain error percent of the mean. Okay, so in other words, there's going to be a confidence interval around the mean calculation, and once it lies within a certain fraction of that mean value that's computed, it will stop the replication. So we'll do replications enough to develop confidence as to how statistical confidence about the value of the simulation experiment for those parameter values. So here, you know, perhaps we have 80% confidence intervals here, and we want it to lie within a certain fraction of the mean, and it will continue doing replications. Maybe here it's after 5, after 10, and these statistics are from dealing with statistics on computations in the mean based on values drawn from a distribution. So we keep on doing these replications until these confidence intervals lie within a certain variability around the mean. Okay. So this is using a box plot where we show the maximum and minimum values. Here we're showing the confidence intervals and the values denoting a certain area within the mean. So, ladies and gentlemen, this error percent corresponds to the red values here, and the confidence level corresponds to this broader confidence interval. We're waiting for it to lie within the red values, this error percent. Okay.
What sort of distribution is this?
This is a good question. I went and I studied it once, and I believe it assumes that it's normally distributed. But I have to go back and double check that. It may actually be robust under different assumptions about that. I figured it out once when I wore a younger man's shoes, but I don't happen to remember at the moment. So it's a great question to ask. Discrepancy. Yeah. So it determines that objective function. So for each realization, that objective function is computed. So to be clear here, for each of these guys here, this objective function is computed, and then it's going to take the mean of those over the different realizations and use that to as part of this calculation for throttling these things if wanted, or just to use it to judge the desired, you know, the discrepancy associated with that particular point in parameter space. Does that make sense? Okay. Okay. Right. So here we ended up enabling random we ended up enabling multiple realizations. Now here I inserted some code to report using trace.ln for a particular realization what the difference was. I just call off to difference, and it computes. So this is once the information is from the main has been sucked out and retained. I call compute the difference. It computes the difference accordingly, and you'll notice that that no results. Well, okay, so initially it's being run for different realizations. No results appear. Eventually, results will appear after a count of runs equal to the replications per iteration. So to report the best payoff. And one thing you'll find is if you do this, this payoff is the mean of the payoffs for the different replications. So it's doing these different replications. It's computing the difference for each of them. It's taking the mean of those and reporting it as the objective function for the first iteration. Okay. In other words, for that parameter vector. Okay. That's where that comes from. Okay. I think let's just write. It turns out I'm not going to try to go into this because it's too substantial an issue here. Perhaps I'll make some comments on this in the next lecture. So calibration is tricky. Calibration helps us learn, but calibration is a challenge. And one thing you have to realize is you sometimes feel like you're wrestling with the model. You often find that it's not according with all the data you provide. Maybe you can get it to accord with some, but then it pops out and doesn't accord with the other. It's like squeezing a balloon. Squeeze here, pops out there, vice versa. Turns out that adding in constraints enhance identifiability. In other words, enhance our ability to identify clear parameter values that are more likely. And adding parameters conversely leads to a larger space to explore and can lead to an underdetermined situation where it's not identifiable. We can't pin down values. There's just not enough data to pin down the requisite values. And so I've built up through many encounters with calibration and cohorts, and I built up a set of tools that I bring to a calibration problem that work pretty darn well and sort of helping to get to the root of the issue. And I've tried to encode some of these in some of these slides. But basically they involve doing experiments that help us learn what's blocking it, why it's blocking it, and help us investigate ways to get around it. And ways to sort of explore what's going on in effective ways. Another final thing you want to do is check uniqueness. Okay, so to get out a best value, is that just one of many values that are nearly that good? Maybe it's just, the highest in a peak on a ridge, and there's many buys all along that ridge that are nearly as good. You don't want to privilege this particular one. And you'd like to know, are these ones that are pretty good? Do they trade off in some structured way? Maybe they tell you in general, maybe not a particular value for the parameters A and B, but maybe they say if A is higher, B can be lower, and vice versa. Often we want to understand not the results of one particular point prediction from calibration, but the results of many calibrations, seeing how the values vary, sort of in a response surface sort of way. We want to look for parameter values at the edges of their permissible ranges, because often it indicates a problem, that if you were just outside, maybe you would get even better. And you really want to scrutinize that. Sometimes, well, I think I won't go into this, but sometimes you need to capture interactions between parameters. And we talked about this early on, differences between calibration and regression. So those are all my comments for today. Next week, we're going to be spending 2 lectures on one of the simultaneously most useful, most practical, most deep aspects of modeling in general, which has to do with the issue of dimensionality. Understanding dimensional structure of quantities and using that. We gave some hints as to how it could be used, for example, to reduce number of parameters in calibration or or parameter variation. And that alone is enough to merit its use. That alone is enough, is a strong virtue to recommend it. But it turns out that there's much greater benefits yet that can come from error checking in models, also benefits in terms of creating scale models. And when it comes to agent-based modeling, where we have real performance challenges associated with us, we will see how we can use dimensional analysis to create scaled-down models, which involve smaller populations. So if you want to understand how flu would spread in Canada, you don't have to simulate 30 million agents. You can simulate a reduced scale model, similar to how aeronautical engineers might work with a reduced scale model of an airplane to do tests in wind tunnels, so they don't have to build a full plane. You can build reduced scale models. And we'll see how dimensional analysis provides a principled way of doing exactly that. The techniques of dimensional analysis, it can hardly be overstated how deep they are and how much they can contribute, from everything from discovery of laws about how variables relate to practical issues like helping models to run faster and catch errors in models. So we'll be spending 2 of our remaining 3 lectures on this topic. Okay, and I'll pick another topic to hit on the final lecture. But that's all for today. I will see if I can have, because I know problem set will be due. I released the problem set yesterday or last night, and I would suggest that you get a start on it soon if you're going to do it. It's one problem, but it can be challenging. You know, you want to make sure time is budgeted. I'll see if I can have 2 office hours next week to make sure you have time for consultation between projects and the problem set. Okay, that's all for today.